In this lecture, we will look at how to draw an NFA for a given regular expression. So let's look at the examples we have discussed. Let's look at the first example of 0 star. So whenever we see the clean closure, the first thing we do is we draw the automaton for what is contained in the clean closure, that is 0. So what would be the automaton for accepting 0? So we have a start state and we have a single final state, right? And this accepts the string which has a single 0. Now we look at 0 star. So when we look at 0 star, the first thing that we need to do is we create the final state to be the initial state, right? We create an initial state which is the final state. We have an epsilon transition to the start state of the automaton for 0, right? Let's label this as Q2, and we have transition from Q1 on an epsilon to Q0. Okay, so this particular automaton, this NFA, accepts 0 star. Why? When we start, we are already in a final state. That means we accept the empty string. We may have a single 0 which can be accepted by taking the epsilon transition and the transition from Q0 to Q1, or two zeros, Q2 to Q0 to Q1, and loop back Q0 to Q1, and so on. The next example is 1 plus. So how do we draw the automaton for 1 plus? Right. So for 1 plus, what we do is 1 plus accepts one or more occurrences of the regular expression 1. So let us draw a regular expression, an NFA for the regular expression 1. So you have the following, right? Okay. So this particular NFA with the final state accepts 1, assuming that this is the start state. Now to accept more ones, what do I need to do? All I need to do is I need to add an epsilon transition back from the final state to the start state, and that will accept 1 repeatedly. Okay. So whatever regular expression is here, right, R, if I have a finite automaton which recognizes R, all I need to do is have an epsilon transition from the final state to the start state. So let's try and draw an automaton for a more complicated example. So let's choose this particular regular expression. So we have 0 followed by, we have 0 followed by 0 or more occurrences of any symbol in sigma, right? So if sigma contains 0 and 1, so I can have 0 and 1 on the transition. The comma indicates OR here, followed by a single 0. The other automaton we have to draw is for 1 sigma star 1, which we draw in a similar fashion. Okay. Or we have a single 0, or a single 1, Okay. And then we have the union of all of these. Please note that these last states are the final states, although I haven't marked them yet. To achieve the union of all these languages, we use the notion of non-determinism. How do we do this? We do this by adding a dummy start state. So this is my dummy start state, and I have an epsilon transition to the start state for each of the automatas for each component of the union. So this was my component of the union, this was its start state, so I have an epsilon transition. This is a component of the union, another component with start state, and so on. Similarly, I have a dummy final state, and I have epsilon transitions to the dummy final state from the final states of each component automata. Alright. So how will this automaton work? The automaton will non-deterministically choose to follow any of the 4 paths from the start state. If my first symbol is a 0, it can either follow this path or this path. If it follows any of these 2 paths, it will immediately get rejected because neither of the states has a transition on a 0. So once it follows these 2 paths, the next state will decide how it should proceed further. So if any path succeeds to take you from the start state to the final state, the automaton will accept the word. And since each automaton accepts each component of the union, you are guaranteed that at least one of the automatas will accept a word if it is present in the union of the 4 paths.